Number 14. So 6.6 was where we did the NAB. Normal approximation about and this is, what's the big deal with this one? What's the main idea with the NAB? What's the only real tweak we have to make? What has to change possibly with the, well, definitely what has to change in the problem when I'm doing a normal approximation to a binomial distribution? What has to change? What do I have to correct for? No, that's not a question. Okay, all right. Yeah, continuity correction, right? I have a discontinuous thing, a discrete data set. 1, 2, 3 people, and I'm trying to pretend like it's continuous. So the best way I could do that is to say, no, it's not really 1. It's actually 0.5 to 1.5. And that runs into 2, which is actually 1.5 to 2.5. So that now it looks continuous. And that actually translates into a better approximation. We saw both ways last time. We said, what if I did it the right way, and what if I made a mistake? And the mistake was way off. Right? So number 14 says, well, number 14 gets right to the point. N equals 12, P is 0.8. And they want to find the probability of 9. And they say part A says find the probability using the table. And I would say, or if you want to, you can always use the formula. I don't see a damn thing wrong with that either. So you can use the table in the back, or you can use the formula. So part A should be pretty straightforward, I would hope. By this point, we have 12 things. I want to get 9 of them. 0.8. I want 9 of those things. What would the probability of failure be? What would Q be? 0.2. Success is 80%. Failure must be 20%. And how many of those do I want? 3. If I have 9 successes, the rest must be failures, and I got 12 total. So that's 3. All right, so you can do that work there. Part B says use a normal distribution if possible. So you have to check, is it good? What check do I do here to make sure that a binomial is normal enough? What do I have to check? And they pretty much tell you actually in the write-up. Yeah. And I always forget this book says greater than or equal to. Kind of depends on which book you use if it's the equal to in there. So NP and NQ have to be at least 5. 12 times 0.8 is who? If I do NP, 12 times 0.8, what do I get? 9.6. So NQ is going to be 12 times 0.2, but that's only 2.4. That's greater than 5, check. That is less than 5, oh crap. So can I do part B? No, it doesn't follow. It doesn't meet the requirements to be normal enough. Therefore, I can only really do part A's work. Part B, I showed that I can't do it that way. Does that make sense? I mean, it's got to be normal in order to use a normal approximation. It's got to be normal enough. And this was not normal enough. Okay. Was that the question on that one? You didn't understand part B, maybe? Okay. Anything else from 6.6? You guys are like, well, once I get there, Jeff, I probably will have questions. That's all right. One more.
Number 10.
Let's see. Use the continuity correction to describe the region of the normal distribution that corresponds. Okay. So if I want, so this is all about the continuity correction. So if I want from 10 to, what does it say, 16? 12 to 16, sorry. If I want from 12 to 16, inclusive, so I want to include 10 and 16. So it's the probability that it's between 12 and 16, including 12 and 16. You guys with me? From old algebra days, that would be 12 to 16. Interval notation, inclusive. So I want to include 12. I want to include 16. So this probability question would be like this. Is that cool? Include 12, include 16, between 12 and 16. So the whole question now is both of these have to change. If I want to include 12 and include 16, well, relative to 12, which way am I going to shade? Up or down? I'm going to shade up because it's in between, right? I want to shade in the middle here. Do I want to start that side or that side? Do I want to start on the right side or the left side? Left side, because I want to include 12. So what would this become then? 11.5. So through the continuity correction, this becomes a probability 11.5. Now what am I going to do with 16? I want to go all the way up. Do I want to stop there or stop there? Front wall or the back wall? The left side or the right side?
Right side.
The right side. I want to include that bar. Don't let that be such a big deal. It really isn't. Do you want to include the bar or not? So if you don't want to include it, you stop. If you do want to include it, you go to the back wall. It matters which way you're shading, but don't try to memorize, well, I'm shading up. No, screw that. Just take a second and say, I don't want to stop there. I want to stop there so I get the whole bar. So that takes me up to 16.5. So that's the continuity correction. Says take this, make it this. And then if there was an actual problem here, you would make a z-score there, make a z-score there, look up the areas, subtract them. Same old process. Once you make the adjustment, it's the same process. That's the beautiful thing about this. Same thing with central limit theorem. Once you change the standard deviation, it's the same process. Okay. I'll tell you what, if I focused more in here on pot odds of poker, you guys would kick ass in that world. I don't want to let you know how I feel, Jeff. Any other questions from 6-6? You would not need glasses, is what I'm trying to say. Okay. So I'll let you, the rest of you guys, get into that section and see what you think. So chapter 7, we are momentarily skipping section 7.2. And the reason I do that is because 7.3 actually flows from formulas we already have. 7.2 doesn't. So, last time I tried to do a very quick introduction of the idea in this section. So somebody help me out. Last time we did something like this. I think we did exactly this. I can't remember. If I wanted to catch the middle 90% of a normal distribution, how far out would that lead me to go? I think we did this at the end of class last time. How would I find that? I want to find these two z-scores, and that tells me how far out to go, right? This is what z-score is a measure of distance. So how do I find that z-score there, for example? Yeah, the chart only understands areas below. If I look up 0.90, I'm going to get this z-score here. That has nothing to do with that picture. I don't want to look up 0.90. That doesn't make any damn sense. I want to look up an area that's below something I want. Well, what area is below that? 5%. Why? There's 90 in there, there's 10 out there, there's 5 out there. Right, the symmetry, I just cut it in half. So if I look up 0.05, that's the one that led us to 1.645. If that's negative 1.645, that must be, again, symmetry kicks ass, right? So what this is really saying, if I have a normal distribution and I go up this much from the mean and down this much from the mean, I catch 90% of the information. All right, that's old stuff, right? This directly leads into this section, though, section 7.3. If I wanted to take the next step and make these into raw scores, what formula must I use to make them into x's? Currently, they're z's, right? These are z-scores. How do I make them into x scores?
Mean plus.
Exactly. So I use this dude. That's old stuff. Here's the new stuff. And here is not really new. It's just being more honest. In statistics, do I normally know the population mean? No, so what can I use instead if I don't know this? I can use the... What do we normally take in a stats analysis? We take a sample. So instead, we don't normally have the population mean, we normally have the sample mean. So if I put X bar there. Now somebody help me out. To get X bar, I must have taken a sample. The minute I take a sample and I'm talking about the means, what has to change? Standard deviation has to change. We just got done talking about that, right? So I can't use this here. I need to use that. How we doing so far? So this is the formula that we know. This is the formula that I keep reading in English, trying to get you guys to realize you can do the same thing. And it's a very simple formula because it's the z-score definition. That's the question I keep asking you every test. What does the z-score mean? This tells you what it means. So it's the same formula we've done before. It's just that I don't normally know that, so I use this. In order to get this, I have to take a sample, so I must change that. And what do I really want to do? I want to go up and down, don't I? I want to go up so many and down so many. This, same amount both ways. So it's going to be plus or minus z, and the standard deviation now is that. So this is what we use. In statistics, what I normally want to do is I want to take a sample. I want to get a feel for what the population is doing, right? So if I took a random sample of 1,000 Grossmont students and found their average age, I'd feel pretty good about that finding. You with me? If I truly randomly selected 1,000 Grossmont students and I got their average age, wouldn't you believe that's got to be close to the real average of everybody at Grossmont? You with me? By itself, though, it's not enough. I need something that tells me how good is that. So what this is all about here is if I take a sample and I find the sample mean and I calculate this, what this gives me is what's called a confidence interval. And so I could say something like the mean is 10, give or take 0.7. That's really what this is. The mean is this, give or take this. You guys see how does that match? We say that sometimes in real life. Well, I'm going to be there about 3 hours, give or take half an hour, depending on traffic. Basically, you're just given this kind of format, right? So stats is saying, if you guys can do it, I can do it too. Nah. We're getting closer to that whole thing about 44% of people want to vote for this guy, and at the bottom is plus or minus so many percentage points. This is not quite that formula yet. This is section 7.2 would be that, where I talk about percentages. This is getting closer to that. So let's try an actual problem before we go crazy with Jeff talking about theory. We take a sample of 87 Grossmont students and find a mean age of 24.9 with sigma known to be, what makes sense? Who cares? 10.13. You with me so far? So you can kind of tell what they have to give you in the problem. They actually have to basically give you all of this stuff. So then you can plug it in and figure out what everything is. This is not an equation. Do you see what I mean? This is not equal to something. I can't solve. I need to know every damn thing in here. So they just have to give it to me. Yes, sir?
Some standard deviation.
Known to be.
Oh.
The thing that 7.3 is still not entirely honest. Because what does this formula have in it that I shouldn't at the same time know? If you were cool with me saying we don't normally know mu, we normally know x bar because we have a sample. What's still in this formula that we shouldn't know for the same reason? Z is fine because Z is going to give, if I want to be 90% confident or 95% confident, I can figure out the Z score. That's fine. I haven't finished this problem out. Sigma. Right? If I don't know mu because I don't have a population, I shouldn't know sigma either. But very often in math, we want to introduce a simpler process, and then we say, well, here's how it gets more complicated if you're more real to life. Sometimes we'll know this. Sometimes we will know this. So this is not completely crap, right? Sometimes we can do this. Most times we don't have a freaking clue that. And that's where 7.4 comes in. We'll get there eventually. So finish this out. I would say here, create the 90% confidence interval for the true mean age of gross mod students. Oh, yeah. My writing is awesome today. All right. You've got to listen to me as I go along. So create the 90% confidence interval for the true mean age of gross mod students. So this, on day one, I was talking about this. What do we do in statistics? We take a sample to get a feel for the population. Now the math is finally there. We're finally caught up to it. We can say, now here's the real math to do what Jeff said on day one. Right? An average by itself is not really enough. I want you to give me a give or take. If one guy says, oh yeah, I can get you there in 10 hours, give or take 3 hours, and the other guy says, I can get you there in 10 hours, give or take an hour, I'm going with the second dude, right? Depending on what vehicle he has. But let's say everything else is the same. I'm going to go with the second dude. You with me? Because the other guy might get me there in 13 hours. Screw that. I want to get there definitely within so many hours. You guys kind of with me? So how do I finish this out? Well, the first thing is, for a 90% confidence interval, what's the z-score got to be? So it's the same idea as earlier. We already calculated this. They have to tell me how confident they want me to be. That tells me how far out I've got to go. You guys kind of with me? Okay. So what did we get for that just a minute ago? 1.645. Why do I not worry about the negative or positive? Because it's built in. It's built into the formula here. You with me? So z is just always going to be the number by itself. 1.645 in this case. Okay. Why is it 1.645? Because that's how far out I've got to go to catch 90% of the stuff. So if I find a sample mean and I go that far out, I don't fish, but I often think of it as like throwing out a net. If there's a certain fish I want to catch, if I throw out a bigger net, I'm more confident that I caught the damn little dude. You with me? If I throw out a smaller net, I'm probably not going to catch him. I got to be crazy precise, right? You guys kind of with me a little bit? For some reason, I got castaway in my head right now. So we got the z-score. What did I give you in here? Yeah, standard deviation is 10.13. What else did I give you? Good. The mean, the x bar, because it came from a sample, right? So x bar was 24.9. What else did I tell you? N is 87, which is everything you need. Did I say anywhere in here that this is a normal distribution? I didn't say that directly, did I? Which normally means I can't do shit. But what saves us? What's the key? Sample size is bigger than 30. Right? So either I've got to say it's normal, or the sample size has to be bigger than 30. You guys remember that? That central limit theorem? The bigger a sample gets, the more normal the sampling distribution gets. And 30 was the magic number. It works for most things, right? So N is 87 greater than 30. Check. Normal. Enough. That normal enough thing is going to keep popping up. Because that's huge in statistics. Is it normal enough or not? Now it's a plug and chug. X bar plus or minus z sigma over square root of n. So 24.9, give or take, this many standard deviations. And let me say something that's in the book real quick before we get this finished out. How did we get that z-score again? We did the 90, and then we looked at what area here? 5%, right? And the symbol for the amount of area that's outside is the little Greek fish. It's the Greek alpha. Alpha means the area outside. Are you guys with me? That little alpha symbol means the area outside. So how did I actually calculate the z-score? Did I use the whole alpha to get the 1.645? No, we took half of the alpha. You with me? Alpha here would be 10. So how did I get the z-score? Cut it in half, of course, so then I can look it up. Where am I going with all this? There's several little things I don't like about this book. And when you look up this formula in the book, it's got this. And that just confuses the hell out of people, and I don't blame you. But all that freaking means, that's not, you don't plug something in there and use it to calculate. That's z sub alpha over 2. That's not part of the equation. That's the z-score that relates to your confidence interval. They didn't need to put that there. I wish they wouldn't have put that there. You guys kind of with me? So this z-score we got here is actually z alpha over 2. That is 1.645. Okay. Cool, cool, cool. So now it's just a matter of what I would suggest you do is do that piece first. And then you can add and subtract it from this. This piece, hopefully not surprisingly, this piece is called the error. Because this is how much I think I'm off by, right? It's this, give or take this much. This is called the error. So what do you guys get when you try to calculate this, the error by itself? Error. To catch up to you, you're probably right. Yeah, I get, say again. 1.787. I like it. 1.787. Can you guys get that 1.787 roughly? So it's just doing this piece, 1.645 times 10.13 divided by square root. Just that piece. I always love it. I have had students come up and ask me where the plus or minus key was on the calculator. Just a quick way of writing two things at once. So now this amount, I can add it to 24.9, I can subtract it from 24.9, and that'll give me an idea of what I think it's between. So what I get when I do those two things, what do you guys get for the lower part? 23.5. Yeah, 23.1 to what's the upper part? So 24 minus this is 23.1, 24.9 plus this. 26.7. I like it, 26.7. And it's fine to go the same decimal places you're given, that's fine. Okay. Again, this is true about statistics all the way through. There's not really any algebra here. The actual math is not difficult. It's just the idea behind it. What do I use? Where do I put it? How do I get the z-score? Where does this thing come from? That's what's hard about statistics. And you're going to love this last part. Chapter 7 and Chapter 8, you're going to have to write a conclusion. Oh, yay. So here's how this conclusion is worded. We are 90% confident that the interval 23.1 to 26.7 years contains the true mean age of gross month students. Oh yeah. Again, one of the most important parts of statistics is being able to realize what the hell you just did. Even more important than algebra, because this normally involves real-life data to understand what the hell you just did. So if I guessed an age between there for the average age, what's the probability that I'm wrong? 10% chance I'm wrong, because I'm 90% confident that this interval catches it. Notice I didn't say we are 90% confident that the real mean age falls in there. If you said that, I'm not going to ding you, but semantically it's wrong. Because the mean doesn't fall somewhere. The mean is somewhere. There is currently an average age of gross mine. It just exists. And I take a bunch of different samples and I say, well, this one catches it, and this one doesn't catch it, and this one catches it. So this interval would catch it 90% of the time, is really what we're trying to say. So be very careful. You want to do it like this. I won't take points off, but try to get it worded like this. Okay. So let's do this. Take a second to figure out, if I ask for a confidence interval of 99%, can you figure out what Z would be? If I ask for a confidence interval of 80%, can you figure out what Z would be? Try to do those two real quick. Does anybody remember empirical rule? It said within 3 standard deviations there was what percentage? It was 68, 95, 99.7. So this should be close to 3. That makes sense. It should be a little less than 3. It doesn't catch 99.7%. So if you're getting something close to 3, relatively close to 3, you're doing pretty good. So how do I do this? This first one here. What do I actually want to look up? If 99% is in there, what's alpha? We use this relatively new. Alpha itself is 1%, so 0.01. Alpha is always the area out in the tails. Let me go ahead and say that. If I say tails, does that make sense? The confidence interval makes tails outside. Alpha is the area in all the tails. So what area do I actually want to look up in the z-score chart? Beautiful, half of that, so 0.005. And if you do that, you should end up on an asterisk. Right in between 0.0045 and 0.005. Where am I at? There it is. Where are you? There you go. 0.0051 and 0.0049. Right in the middle of that is what I want. If you follow it down, you get 2575. So the z-score would be 2.575. So that's the one I would plug into the formula to get this interval, right? So would a 99% confidence interval be bigger or smaller than a 90% confidence interval? It'd be bigger because the z-score would be bigger, which makes the error larger. And it only makes sense. If I want to be more confident, I'm going to have to throw out a bigger net. My interval has to get wider, has to get bigger. What about 80%? Same idea. If this is 0.8, alpha would be 20%, so then I look up half of that, 0.1. And if you look at 0.1, I think you should get 1.28. That's all right? So the z-score you would use would be 1.28. Cool. I want to sneak in one more thing and then I have a handout. Let's see if I can do this. How's this feeling so far? It's using an old formula, the mu plus z sigma. It's changed it a little bit, x bar plus or minus z sigma over square root of n. It's the same formula, really. But I find a z-score based on how confident I want to be. Yeah?
I'm confused on where you got the 1.6.
The which one?
The 1.28.
Oh, the 1.28. If you look up 0.1 in the chart, the closest I get to 0.1 looks to be...
Oh, the area you're finding?
Yeah.
Oh, okay.
Because that 0.1 is an area, right?
Okay.
So be careful. Don't look at 0.010 on the z-score because I don't know the z-score yet. Cool. And it's real easy. Trust me. These look like freaking z-scores. So they're evil. Don't let them be. You know it's an area. Now, probably the most interesting part of this formula ends up being this part. Let me write it by itself. Because this tells me how far off I am. And if there's a part of a formula that relates to something, I can control it. If I want my error to be small, I can just set E to that small number. And then what can I solve for? I'm going to know Z because I know how confident I want to be. And I know sigma because that's given to me. So I can actually figure out how big my sample has to be. If I want to be really certain about something, I want my error to be very small, my sample is probably going to have to be really big. The bigger my sample, the more confident I am. So the really cool thing about this formula is it's finally telling us what we knew on day one. The bigger a sample I take, the more sure I should be about what I see. And this is saying exactly that. The bigger my n gets, the smaller my error gets. The more sure I am about this dude. So here's the funky thing. Here's the little tiny bit of algebra. Another day with a little bit of algebra. Right? Can you solve this for n? I like that you're all looking this way. I was hoping somebody would actually start writing something. I don't know. Do you guys have an idea of how to solve this for n? What sucks about where n is, considering I want to solve for it? It's on the freaking bottom, so how do I take care of that? Multiply by it. That brings it up, right? So if I multiply by root n, that goes away. And then the only thing I have to take care of now is the stupid e, and then I got to get that root out of there, right? So if I divide by e, and how do I get rid of the root?
Square it.
Yeah.
Square both sides. So you see this either as z sigma over e squared, or you see it as all of them squared. It doesn't matter. No, Jeff. Same thing. That's just algebra. Now, this really is a feasibility study. Let's say your boss says, I want you to go take a sample and I want you to be within $30 of how much money you think we're going to make next year. You're like, oh shit, okay. And it turns out that your sample has to be 80 billion big. And you're like, boss, that's not feasible. Could you maybe ease up a bit on the tolerance level? Can I be off a little more? So it's a feasibility study. If n turned out to be 300, okay, I can do that. If n turns out to be 100,000, oh shit, I might need some help. Look at it, 100,000 things. Yeah.
What does E represent exactly again?
Error.
Okay, so E is error.
E is error. I love it. So that's why I said E equals this, because this is error. Cool. Yes, ma'am.
Is this just like check them, or what is this?
This is a problem on its own. And when they say find the sample size you need to be within so much, what's the key word in there that tells me the error within? If I want to be within so much, that's how off I want to be. So let me give you this handout, and I'll show you exactly what I'm talking about. got to work on this thing together. Part A and Part B. And then we'll see if I end up with any time left. Don't get very hopeful. This is not how it's going to look on a quiz or a test. I won't be that explanatory. But, for right now, it will be. So we take a sample of 22 men and find their average height to be that. Heights are known to be normally distributed with population standards. Why did I have to say that heights are known to be normally distributed? Why did I have to say that? Yeah, my sample size is not big enough to guarantee it, so I have to know it going in. Cool. So 1A, find the 98% confidence interval. Okay, so let's first figure out what I already know, and then I'll figure out what I don't know yet. What's X bar? 68.9. What's sigma? 2.8. I love it. And what's N? 22 men. And then how do I find Z? For confidence interval, the Z always comes from where? Yeah, how confident I want to be. The percentage confidence I want to have. Here I want to be 98% confident. So if I want to be 98% confident, what's alpha going to be? 2. So then what am I going to look up? 0.01. Yeah, 2%, 0.02. Half of that is 0.01 to be on that side. If I look up 0.01, you should get negative 233. You can double check me. By the end of the semester, you'll have some of these memorized because they happen a lot. 90%, 95%, 99%, 98% is one of them that happens often enough too. So my z-score is going to be 2.33 that I want to use in the formula. So now I just got to plug and chug, right? I give you the formula on there. X bar plus or minus z sigma over square root of n. So X bar was 68.9. Give or take this many standard deviations. So first figure out what the error is. Bless you. Bless you. So what do you guys get for the error? Yeah, like 1.4? It's okay to round to the same number of places that one has. So now my confidence interval, now I just have to add that, subtract that from 68.9. So if I subtract it, I get down to 67.5. If I add that, I get up to 70.3. So how would you say the phrase at the end, the conclusion? Good. We are 98% confident that the interval 67.5 to 70.3 was it years? No, inches. Heights. Contains the true mean height of dudes. So we are 98% confident that that interval we just created contains the true mean height of men. So any interval that you make, 2% of them will not contain it. 98% of them should. So I feel pretty good that mine contains it. Only a 2% chance it doesn't. Now before I let you go, I want to do part B based off of what we just did here. Part B says, how many men? That is a huge clue. Got a raging clue. This is a huge clue. I know I want to use I know I want to use the formula that has n, that's solved for n, because I want to know how many. I want to know the number. How many men to be within 0.5 inches. And that I've underlined that word within because that's the clue to know what the error is. That's the key word. So it's the same problem. So I know going in that sigma is 2.8. I know that Z, I'm still at 98% confidence, so Z is still 2.33. And I know my error, I want it to be, that's right, half an inch. Right? I want to be within 0.5 inches, so I know my error is to be 0.5 inches. Now, what was my error over there at 98% confidence? What was my error with 22 then? Yeah, 1.4. So I know to make it go all the way down to half an inch, my sample's got to get a lot bigger than 22. So far, so good? So now, if I use my formula, n is z squared, sigma squared over e squared, just plug and chug now. N is z, well, 2.33 squared times sigma squared. Sigma is 2.8. And I want my e to be 0.5. The biggest mistake I see is somebody forgets to square something. And what do you get?
25.
Yeah, 170.25, and you always round up. 170 would not be enough. This says you have to have at least this many to be within half an inch, so you better go up. You always round that up. You always are more conservative in these problems. So that part C I'll leave to you. We'll talk about that next time. I'll have the answer key next time. So just so you know, homework, all of Chapter 6, but only Section 7.3. Only Section 7.3. You don't have to do 7.2 yet or 7.4.
Wednesday, we'll have our quiz back on Monday.
I'll give you the quiz back on Monday.
And we'll go over Monday, will that be on the test?
Monday's review day. Nothing new on Monday. If anybody didn't get their last quiz back, you might want to come up and see me. I have several I'm holding on to. Oh, cool.
I still don't understand how to get through.
Oh, you're cool with the 0.01?
Yeah.
Okay, so then now that's an area.
Okay.
I don't know the z-score yet, so areas are always in here. So then you look up 0.01.
Okay.
The closest I can get to 0.01 is that, right? That's 2 away, that's only 1 away, so it's 2, 3, 3.
Oh, okay.
Bam. Yeah.
All right.
Cool.
I was like trying to figure it out and I couldn't find it, but.
Gotcha.
All right, thank you.
Oh, yeah, sure, of course. Yep, thank you.
How come I'm getting 17,000 here?
Dude.
Where's my math? I did these all separate too, and then I did that separate.
Oh, it's not 0.05, it's just 0.5.
Oh,
Yeah.
okay. And then also